law of universal gravitation. So the definition is that every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This force acts along a line joining the two particles. Well, for sure, the equation's much easier than the word definition. Our equation is a force is equal to big G, which is gravitational constant, multiplied by both masses divided by the radius squared. Now sometimes you will see a d squared instead of an r squared. If we're talking about a person standing upon a planet, say the Earth, we're going to look at the radius of the Earth as the distance between the two. If we're looking at two different objects, we'll look at the distance between the two masses. So our variables. It's a force, so it's in newtons. Your masses need to be in kilograms. Your radius needs to be in meters. G is a constant, and that value is 6.67 times 10 to the negative 11 Newton meter squared kilogram squared, which is why your units are dictated for those other variables. Henry Cavendish was the first to measure the gravitational constant. And gravity is a very weak force. What he did was he set up two iron balls with two smaller ones and looked at the torsion of the wire, and torsion is just the twisting of the wire. The University of Seattle has tried to measure it more precisely, but it's still one of those elusive measurements because it is so weak. But you can see the large spheres. Inside is a wire that they look at the twisting, and then this part acts as a pendulum. And that's this pendulum part. There's the wire coming off, and this is their value of G, 6.674215, plus or minus that small amount. But still they say that it's, I want to say, about 0.15% off. Our example. We want to determine the gravitational attraction between a 60 kilogram person and a 1,000 kilogram rock when they are 20 meters apart. So the first thing you want to do is list all your variables. So we're determining the force of gravitational attraction. So let me just underline what we have. So we're finding F. We know M1 is 60, M2 is 1,000. It doesn't matter what you call them. And the distance between them is 20 meters. So F is what we're trying to find. I'll say M1 is 60 kilograms. M2 is 1,000 kilograms. And the distance between them is 20 meters. Now G is a constant, 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. Our basic equation, F equals G M1 M2 divided by D squared. So notice I used D instead of R in this equation. So G is 6.67 times 10 to the negative 11th newtons meters squared kilograms squared, multiplied by your two masses, 60 kilograms and 1,000 kilograms, and divide that product by your distance squared. Don't forget to square it. So, looking at units, we're going to end up with newtons for our force, kilograms there twice, so it cancels with that denominator. Meters will be squared, so those will cancel. Try putting it in your calculator, and your force rounded to 3 sig figs, is 1.00 times 10 to the negative 8th newtons. Put a box around it. I encourage you to put it in your calculator and make sure that you can do it properly. That's usually where the mistakes are made, not in the setup of the problem. My second example, determine the distance between Braden, whose mass is 90 kilograms, and a whale with a mass of 30,000 kilograms if the force of attraction between them is 2 times 10 to the negative 9th newtons. So notice this gravitational force, very, very weak, always a small exponent. So on this guy, we're trying to find the distance between them. So I want to rearrange the equation before I start. So our basic equation is F equals G m1 m2 divided by d squared. So my first rearrangement gives me d squared equals G m1 m2 over F. To get rid of the squared, you're going to take square root of both sides. So your working equation is the square root of G m1 m2 over F. Super important that you rearrange before you plug in your numbers. Be much easier for you. So let's list what we have. So we're determining the distance, and we have Braden, we'll call him M1, he's 90 kilograms. The whale is 30,000 kilograms. The force between them is 2 times 10 to the negative 9th newtons. And G, if you write down these constants, you end up memorizing them without ever trying. 6.67 times 10 to the negative 11 newtons meters squared over kilogram squared. We had our rearranged equation. Let me rewrite it. The square root of G m1 m2 over F. So G, 6.67 times 10 to the negative 11th newtons meters squared kilogram squared. I like including the units so I can use unit analysis to verify my answer. Putting in my two masses, dividing by my force, 2 times 10 to the negative 9th newtons, and take the square root of the whole thing. Move that guy. So put this in your calculator. Make sure you can do the math besides just showing the work. And our distance is 300 meters. Now, looking at unit analysis, I have kilogram, kilogram, that's kilogram squared. My newtons go away. Notice I have meter squared under the square root sign, so that looks good. If I want 3 sig figs, and let's see, what our 30,000 look like? It would only show us 1 sig fig, actually. That's our distance, 300 meters. Our next example. This goes back to how we find the weight of a student, and you'll see the point as we finish up. So remember that weight is just m times g. So Fg for weight is m times g. So 70 kilogram student times 9.8 meters per second squared, and the weight of this student is 686 newtons. I'm going to leave it with 3 sig figs. Now, I'd like us to determine the gravitational attraction between this student and the Earth. Now, you need to know the mass of the Earth and the radius of the Earth. Notice it's in kilograms, so let's go ahead and change that to meters. I'm going to do it in 2 steps. So this is 6.38 times 10 to the 3rd kilograms. And if I change it to meters, I'm going to multiply by 1,000 again. So it's 6.38 times 10 to the 6th meters is my radius. So this time, we're going to find the gravitational attraction between that 70 kilogram student. So F is what we're trying to find. M1 is 70. M2 is the mass of the Earth. That was 5.98 times 10 to the 24th kilograms. The radius of the Earth was 6.38 times 10 to the 6th meters. And our gravitational constant, 6.67 times 10 to the negative 11th newtons meter squared kilogram squared. So we're using the basic equation, G times M1 times M2 divided by R squared. So notice how I just switched it to R instead of D. Okay, putting in our numbers, we have 6.67 times 10 to the negative 11th newtons meter squared kilogram squared times your mass of the student multiplied by the mass of the Earth, 5.98 times 10 to the 24th, huge mass, all divided by 6.38 times 10 to the 6th meters quantity squared. Be really careful putting this in your calculator. There's lots of things that can go wrong, but hopefully you do it all right. Your force, when you calculate, look at that, 686 newtons. So that force of attraction is the same as the weight of the student. So another thing you can do is we can look at finding the acceleration due to gravity of the Earth by saying, because Fg is equal to our law of universal gravitation, so we can say mg is equal to g, and that m being m1, the mass of the person, m1, m2 over r squared. So when you cancel, your m's go away, and here's how we get our final result. We have the acceleration due to gravity is the gravitational constant times the mass of, it could be the Earth, it can be any other planet or moon, divided by r squared.